Okay, hello everybody. Welcome back to Comp 3430 Operating Systems. It is the last week. It's the last week of classes. Yeah, at least for this half of summer. I hope that you all had an excellent, if not a little bit rainy weekend. I was able to get to the zoo again. This is a popular destination for my family. And I learned something new, which I thought was really cool. One of the things that they have at the Winnipeg Zoo, and if you've never been to the Winnipeg Zoo before, the Assiniboine Park Zoo, because you're not from here or just because you are an adult now and you don't have children and you don't want to go to the zoo, you don't need a child to be a child to go to the zoo. There's a lot of cool stuff that they've got there. One of the things that they've got at our Assiniboine Park Zoo is polar bears, which is not unique. I think there are other zoos that have polar bears in them, but this is a little bit closer to their natural habitat. And one of the things that I learned about at the zoo this weekend regarding the polar bears that are at our zoo is that they are being used right now to help try to get a system set up so that people studying polar bears can measure how much a polar bear weighs by just taking photos of it from the air. They don't really want to like tranquilize polar bears in the wild too often just to get weight measurement, and so they're able to use our polar bears for this because our polar bears are trained to go and get on the scale. It's like good treat time, basically. Like, here's a treat, and then they can take photos from the top and photos from the side. And then when people who research polar bears are like zooming around in helicopters up north, they can just take photos from the top and try to estimate the weight of a polar bear, which I think that's super cool. I think that's really, really cool. It's also the Assiniboine Park Zoo is a place where you can go and have lunch and like basically sit and watch polar bears in a field being kind of lazy or playing around with stuff, which is I think that's pretty cool. The food is terrible, but it's a unique place to actually go and sit there and do that. So if you've never been to the Assiniboine Park Zoo, if you get a chance over the summertime, take the chance, take the time to go. It's a good place to be. Yeah, I otherwise hope you had a great weekend. Today, what I want to do is I want to revisit one of the scheduling policies, not revisit the scheduling policy, but rather actually visit the scheduling policy. We're going to be taking a look at MLFQ, and I'm going to go through the process of kind of stepping through it. I've got like additional paper copies of this up front, so if you don't have the one that you got from last time, please feel free to come and grab one. But I've also put an additional copy of an updated version of this scheduling policy up on the course webpage. So we're gonna work through that together, and I'm gonna need to get to that right now because I realize as I'm asking you to pull up yours that I didn't bring up my own. So I'm going to find that under today's lecture here. And this is what my updated version looks like. And so I'm going to put this up here when it gets to be time. But I've done some minor changes to the tasks that we've got here. But I'll show this up again when it's time to take a look at that. The other thing that I want us to be able to do today is I want us to start thinking about virtual memory. So this is kind of the last major topic for this course, is this idea of virtual memory. And this is the part of the course where we're going to start to tread on another course's toes. We're going to be starting to look at this idea of virtual memory, but with the understanding that virtual memory explicitly needs hardware support. And there's a great deal of hardware-related stuff that we'll be thinking about in the context of virtual memory. And we're going to start touching on a different course, which is Comp 3370. This is computer organization. If you've already taken the course, excellent. If you haven't taken the course, that's fine. We're not really going to be spending much time talking about hardware in this course. The hardware is there. We configure it as an operating system, and so we have to keep track of things like what parts of our virtual address space are mapped, where they're mapped, and how they're mapped. So our perspective of this is going to be from the abstract idea of how does virtual memory work? Just generally, like how do I have addresses and address spaces that are much, much bigger than the available physical memory on my machine? And then kind of getting down to the point of what does the hardware need to know so that it can do the translations for me. And that's where I, as an operating system, need to do things like modify my process control block and my thread control block to be able to keep track of what the virtual address space is for a process or for a thread. So I want you to be able to explain how a process's entire address space can be provided by the concept of virtual memory. This is a high-level thing. I want you to be able to describe how the operating system works with the underlying hardware to manage virtual memory. We're going to look at a few different types of implementations of virtual memory, ranging from like the way that virtual memory was 40 or 50 years ago up into what we're doing right now with modern operating systems. And so what the operating system has had to do to be able to support that with the hardware has changed over time. So we'll think about each of those. And then all of them have some idea of partitioning memory, physical memory, or partitioning address spaces, or both. And so we'll think about the idea of how taking these big things and breaking them into tiny pieces will help us a lot. And this is going to get us to the point of effectively recognizing that virtual memory is just another file system. It's another file system, but it's at a different layer of the memory hierarchy that we've got. And we'll take a little bit of a look at that. And then finally, compare and contrast methods for address translation. So first things first, what I want to do is I want to spend a little bit of time taking a look at the multi-level feedback queue. I'm not going to calculate turnaround time and response time for that. I believe that these are tasks that you ought to be able to do at this point, given the information that we had in the last couple of classes and what's in our textbook describing this. I want to think a little bit about the fairness of this policy in terms of how it works, but I do want to mechanically schedule some tasks with this. And so I'm going to pop over here to my PowerPoint slides, and I'm going to zoom in a little bit here so that you can have a better view of what the tasks are. This is just going everywhere. I'm really sorry. I'm going to zoom in a little bit by clicking on this button instead of scrolling wildly around so that you can see what these tasks look like and the properties that they have. The major change that I've added to the tasks beyond the amount of time that they have remaining and when they arrive is that I've added 2 additional properties that we're going to have to keep track of for these tasks. The first one is the amount of time that this task has spent in a queue, where the FIFO round robin shortest job first, shortest time to completion first. All of these policies are effectively dumping all of our tasks in exactly the same queue. The idea with the multi-level feedback queue is that we're going to have several different queues at several different priorities. So one queue will be the highest priority queue, and then another queue will be the lowest priority queue. There will be some possible queues within there. And the way that we're going to be pulling tasks off of these different queues is based on the priority of the tasks that are in the queues themselves. I'm going to pop open our textbook just below this so that you can have these task properties open as you're looking at this. And I wanted to draw your attention to this chapter in our textbook that describes the idea of the multi-level feedback queue. And I'm going to skip past a lot of this stuff in terms of getting us to the point that we want to get to here. But the basic idea of a multi-level feedback queue is this, where I'm going to have a bunch of different queues. I'm going to be putting my tasks into these different queues, and I'm going to be moving them around based on the way that they behave in the system. So how much time they are spending on the CPU at any given time. I'm going to scroll down even further, and the ultimate description of the multi-level feedback queue here describes these 5 rules, or these 5 rules that describe how the system should work. And that's way down here. Right there. So we're going to have a series of different queues. The number of queues that we have in the system is a setting. There's just a big puddle over there under a pipe. Awesome. The number of queues that we have in the system is something that we can configure. So this would be something that we make decisions about as we're starting up the scheduler. For us in this class, for this example right now, we're going to have 2 queues. We're not going to have any more queues than that. There's going to be exactly 2 queues, but the number of queues that you have are going to be decided based on the kinds of system that you've got. These rules collectively describe how tasks should be moved around within the queues that we've got based on measurements that we've taken about their behavior as time goes on in this system. So the first rule here is that we have multiple priorities. If I have any 2 tasks, A and B, if the priority of one task is higher than the priority of another task, then the higher priority task goes first. That's the one that we pick. There's 2 tasks that have different priorities. We pick the one that has the higher priority. If tasks have the same priority, and so in the context here, this is they are in the same queue, we just do round robin on those tasks. When we add new tasks to the system, they're always at the highest priority. So anytime a new task shows up, it's always going to go in the highest priority queue. A task is going to be allowed to spend a certain amount of time holding the resource while it's in that level of a queue. So here it says, once a job uses its time allotment at a given level, its priority is reduced. So that does not mean that it's spent this much wall clock time doing stuff, either running or not running in that queue, but rather it's spent this much time actually having the CPU in this queue. So every time we put this task onto the processor, we're going to measure the difference of how much time it had from when it got on the CPU until how much time it was that we took it off the CPU. It was interrupted or it yielded the processor. That's how much time we're going to measure to say how much time it's had the processor or the resource at that priority level here. Once it exceeds this time allotment level, then we're going to down prioritize it. So it's used up too much of its processor time, or it's used up how much processor time we've said it's allowed to use up at this priority level. So we're going to shove its priority down so that other tasks get access to the CPU or the resource that we're scheduling. At the very bottom of this rule set here is this idea of priority boosting. And the way that this works is that after some other constant, so time period S here, I'm going to take every job in the system and put them back into the top queue. So jobs enter the system at the top queue. I do round robin of the top queue because everything's at the same priority initially. As time proceeds, I'm going to start moving these processes and tasks down to the next lower priority because they're going to spend time using the resource that we've got. Once we run out of tasks at the highest priority level, we're going to go down to the next priority level and do round robin on that. And once we run out of tasks there, we're going to go down to the next priority level and do round robin on that. And then eventually, after a certain period of time, we're just going to push everybody back up to the top again. Some properties of this are things like the response time for tasks entering the system should be pretty much perfect every time, because every time we add a new task to the system, it's at the highest priority. It's always going to get the CPU really soon after it enters the system because it will have a higher priority than everything else that's already been in the system for a long time. Are there any questions about this before I kind of step through this mechanical MLFQ stuff? Yeah.
So I'm just trying to think of the structure of this. So each individual task there has its own queue.
Each individual task in my setup here has a priority. And so every task doesn't get its own queue. We have a fixed number of queues, and then the tasks can be in one of those fixed number of queues as the system is working.
Okay. So
Yeah.
We don't know which queues then or how many queues there are.
We will know how many queues there are because this is a constant that's set when we start the system running in the first place. So in our case, with the example we're going to step through, I'm telling you verbally that we're going to have 2 queues. In the early description in the chapter here, they have 8 queues. I think if you go further down, I think it's actually right beneath this. It says, oh, it doesn't say here how many queues there are. It does say that Windows NT uses MLFQ as the scheduler, but like actual OSs might have dozens of queues in their setup. But for us, we're going to have 2 queues. And so we have 5 tasks here, and they're going to be spread across these 2 queues as the system is progressing. But initially, they're all going to be in the top priority queue, the highest priority one. Yeah. Any other questions about this? Okay, awesome. So I'm going to zoom out here a little bit. And I'm going to start stepping through what would be going on with this. The amount of time that I've allocated to these different tasks is significantly higher than what we were otherwise doing with the queues with the tasks that we had last week. But what I really want to do with this is just kind of see what happens as we step through this, especially as we get to the point of doing boosting of tasks and having to move tasks down in the amount of time that they've spent at a certain priority level. So the time is now 0, so we're going to start this whole system up. At time 0, a couple of things will happen. Again, reminder of some of the unrealistic things that are happening in our system. When things are happening at a time, they all happen instantaneously. So it doesn't take time to do context switching. We're just going to hand wave that away and say that it's actually happening all at the same time here. So at time unit 0, task A would arrive in this system. And so it would initially get put into the current task queue here. Oh, I'm sorry. It would initially get put into the current task queue here. And at time unit 0, because there's nothing else in this system, it would just immediately get access to the CPU. So it would go back, it would go directly to this running task area. It currently holds the CPU at time 0. I would then report the first runtime here and say that it was first run at time 0. And we can then say, again, its response time is perfect. It arrived and it immediately got access to the CPU here. At 5 units of time, we're going to preempt this task. It's going to get kicked off the CPU and put back into our current task queue. We're going to say that it has had 5 units of time on the CPU now. And so I'm going to change the queue time property here to be 5. I'm going to compare how much time this task has spent to the amount of time overall that we allow a task to stay at that priority level. It's still below the queue time allotment, so I'm going to leave it at that priority level. And then in the same instant, I'm going to put it back on the CPU because nobody else is in the system right now. This is the only task that's in the system. So I'll put it back on. We're going to have 5 more units of time go by here. At time 10, we're going to preempt this task. And I'm explicitly saying this now because we have to preempt the task so that we can do accounting on this task. As an OS, I can't do accounting on a task that currently holds the only CPU on the system. I can't do anything if that task currently holds the CPU on the system. So I have to be able to preempt it here. So I'm going to take it off the current running task. At time 10, it has spent 10 total units of time on the CPU. It now is meeting this amount of time that I've said that it's allowed to have on the CPU. And so at this point, I'm going to change the priority level of this task. I'm inverting this just because in my brain, this is how priorities work. But I'm going to say that this has priority 1 and priority 0 is the highest priority that we can have in the system. So kind of like ACES high sort of thing. This is going to be the highest level in our system. The ACES high does not work here at all. I'm just going to say that it's at priority 1. And when I put it at priority 1, I'm also going to reset the amount of time that it spent in that queue back to 0. As I change its priority level, as I physically move it to a different queue, it will not have spent any time holding the CPU yet at that level. At time 10, there are still no other tasks in the system, so I'm going to put task A back on the CPU and let it run a little bit more. There are no other tasks that have a higher priority than it, and so it still just gets access to the CPU. There's nobody else in the system yet. At time 15, several things are going to happen. I'm going to preempt task A. We have to physically take it off of our CPU so that we as an OS can do the accounting for this thing. At time 15, it has spent 5 units of time at priority level 1. At time 15, task B also arrives in the system. And so I'm going to move it down here. But task B is entering the system at the highest priority level. So it's going to get in front of task A here. So all of these are happening at the same time. At the same instant, arriving at time 15, I'm going to say that task B gets put on the processor. So this is now rule 1 of our system. If task, I don't want to use a and B here, if one task has a higher priority than another task, then the highest priority thing gets to go on the CPU. In this system state that we have right now, task B has a higher priority than task A because it just arrived and we put it into the highest priority queue. So task B is going to get to go in front of this. Its first runtime is 15. And again, response time here is perfect. As soon as it showed up in the system, it got access to the CPU. It didn't have to wait around for that to happen. Are we all in the same state so far? Okay. At time 20, task B is going to be preempted. I'm going to record that it spent 5 units of time at this priority level. And then in the same instant, task D and C are also going to arrive in this system. I'm going to put them in front of task A because I'm inserting them into the highest priority queue. They are at the highest priority as soon as they enter the system. I'm putting them behind task B because task B just happened to be here first. But in this state, task B, D, and C here all have the highest priority in the system. These all 3 have the highest priority in the system, and so we're going to do round robin on them. We're going to start doing round robin on these 3 tasks. Yeah. That's a good question. The question is, how do we know which one goes first, D or C? In our case right now, this is an arbitrary decision on my part. I could have put them the other way around because we're using this idea that they're just arriving at the same instant, and so it's kind of an arbitrary order here. We don't really, we can't say that for actual systems because no system is actually going to have like all the way down to infinity precision of these 2 systems. These 2 tasks have arrived at different times. They're gonna arrive at different times. One will arrive before the other one. But in this system, I'm just making an arbitrary choice here. We don't try to measure things like how much time is left here. This is for our own purposes at this point. We're not using how much time is left to try and decide which one goes first. They just have the same priority at this point. Any other questions so far? We're okay? So in the same instant, then task B is going to get to go back on our CPU. And again, arbitrary decision on my part here of what order is actually happening. It might be that task D got to go on the CPU, as long as we keep them in round robin order. Round robin order here is important. It is fundamentally important to the way that this whole thing works. At time unit 25, I'm going to take task B off, but I'm doing it in round robin order. And so I'm going to shove these tasks before it. Task B is taken off. It has now spent 10 units of time at that priority level. And so I'm going to down prioritize this. Now, what you choose to do here is, again, kind of up to you how you make the decision about where to put this task. This could be inserted at the end of these ones in a round robin fashion and then down prioritized. And now it's in front of task A. It might be that you choose to physically move it to a different queue and put it behind task A. It doesn't really matter what order you do this in, as long as once it gets its spot in the line, it keeps that spot in the line for round robin ordering of stuff. So I'm going to say that at queue time at current time 25, that I'm going to down prioritize this to priority 1. And I'm going to set its queue time back to 0, and I'm going to say that it gets to sit in front of task A here. In that same instant, I'm going to put task D on the CPU, and its first runtime is now going to be 25. Its response time is not perfect anymore, but it's still very small compared to some of the other things that we were seeing with some of the other kinds of policies that we had. I'm going to skip ahead now to time 30. And now a bunch of things are going to happen. And again, all in the same instant, but a bunch of things are going to happen here. Task D first is going to get preempted. At time 30, we've met our boost time. And our boost time here says take everything that's in the system and move it to the highest priority level. Put everything back in that top queue. Notice that task A was kind of getting starved here. It wasn't able to get back on the CPU because there were these new things that were getting added to the system at a higher priority than it. And so it was never going to get back onto the CPU if it got stuck at this lower priority level. So at time 30, I'm going to take everything that's in this system and I'm going to change its priority back to the highest priority in this system. So I'm going to change all of these to priority 0. And I'm also going to change how much time they've spent in this queue back down to 0. If I'm changing the priority from 1, a lower priority, to priority 0, a higher priority, if I'm making that change, it spent 0 time at that priority. It spent 0 time at that priority. And so it has to get its full amount of time at that priority in the queue that we're elevating it to at that point. So now we've got 4 tasks. They are all at the same priority level. None of them have spent any time in the queue at this priority. We've just did that boost. And task E will also arrive in the system. And I'm going to put it down here at the end. At this point, we would start to do round robin. All of these tasks are at the same priority level. And so all tasks are going to get a chance to get on the CPU before we consider down prioritizing them or doing a boost at some other point. I'm going to stop here because we've kind of exercised all the different features of MLFQ. But I'd be happy to stop and see if anybody has any questions about this before we proceed with anything else. Yeah. So that's a good question. If we just did the boost, and I'm going to summarize your question effectively as where would we put E based on boosting priority? In terms of arriving after we did the priority boost for these other tasks, and even if we didn't do it, if we did it before, the priority boost would cause it to just stay at the top level. When we insert the new task, it's going to be at the highest priority level. in terms of inserting something to the task queue that we've got here, I'm going to say that when it arrives at the system, it should be inserted at the end of the highest priority level queue that we have. So as this task shows up, it should get put to the end of the queue. Anytime we want to add something back to the queue, it's always going to be at the end of the priority level that we should be inserting it to here. Does that make sense? Okay, awesome. In terms of my implementation of this, I implemented it kind of like the way I'm showing you right now. I implemented this with one queue and just a priority queue. I didn't have 4 or 5 different queue structures in my implementation, partly because I don't want to have to manage physically moving tasks around in the system. I don't want to have to take it out of a queue and move it physically to a different queue structure in the system. I just want to leave them all in the same queue. That makes priority boosting a pretty simple operation for me because I can just then run over the whole list and change everybody's priority to 0 to the highest priority queue, as opposed to having to empty all the queues that are beneath that and shift everything up. The order of operations, so like whether or not you put task E at the end, or if you're priority boosting everything and you have to move one task to some other place in the queue, it's kind of irrelevant. It's an irrelevant implementation detail because the important part of this entire operation is that we're doing round robin at each priority level. Once it has its place in line at that priority level, it will keep its place in line. It gets put at the back, but it always gets put at the back, and then it moves its way toward the front, and then it gets put at the back, and it moves its way toward the front, and it gets put at the back. So I am going to ask you a question. With MLFQ, as we've seen it so far, assuming that we have an arbitrarily large number of tasks, assuming that we have something that approaches infinity in terms of the number of tasks that we have in the system, they're all entering the system at any random time. It doesn't matter when they start. They're just showing up in the system over a period of time. If we can assume that all tasks are fair, they all finish, they will all terminate after some amount of time. Think about this for a moment, and then I'll ask you thumbs up, meaning yes, this is a fair system, and thumbs down, no, this is not a fair system. Assuming that all tasks are fair, is this a fair implementation of a scheduling policy? Does everyone eventually get some time on the CPU? Okay, thumbs up, thumbs down. I'm seeing 2 thumbs up in a lot of cases. Yeah, absolutely. This is a fair policy, assuming that all tasks are fair. If we can assume that unfair tasks exist, so some tasks don't terminate, can we say the same thing? Is it still a fair policy? Thumbs up, thumbs down. Yeah, yes, absolutely. This is also still a fair policy. This is a fair policy in both cases because, in my mind, of 3 important things. One is preemptive. We can take control back of the CPU. We are able to take control back of the CPU and make decisions about which one gets to go next. 2, we're doing round robin. Round robin itself is a fair policy. It might not be the best policy, but it's a fair policy. Every task in a priority level will eventually get access to the CPU at least once. And 3, it's a fair policy because we eventually push everybody to the same priority level over a period of time. If a bunch of new tasks arrive, we're going to boost those lowest priority things up, and they will get access to the CPU again. It might not be fast to get access to the CPU again, but they will eventually get access to the CPU again. So for MLFQ, in my mind, it is a fair policy in both cases, whether or not tasks are fair. Unfair tasks here is kind of broken by the idea of preemption, and then fair tasks or unfair tasks is the other 2 parts of this policy. All right, are there any questions about scheduling before we move on to something completely different? All right, awesome. Okay. With that, then I think what I will do is I'll give you some time to ask questions about assignment 3, and then we will have a little bit of a quiz on virtual memory. So I'm going to hold this up here for a moment. I'm going to time limit the amount of time that we have for questions on the assignment to 10 minutes on my timer. And while you are spinning this up, I'm going to take a quick look at some of the files that I've given you as examples in this assignment. So in this assignment, I've given you a few different examples. NQP printer here, this is a piece of code that I've demonstrated to you, and what it does is it tries to help exercise the minimal implementation of threads here, where there's exactly 2 threads and they just switch back and forth between each other. And the idea is that they want to be able to demonstrate progress being made upon each execution of the thread. Every time you switch to this thread, it should continue counting up as opposed to starting from the beginning. Remember that what we're doing here is cooperative, so we're always going to have this yield operation at some point, and these threads of execution are going to yield after printing out 50 lines, and then they'll yield to the other one, and then they'll yield to the other one, and they kind of switch back and forth based on that. So your scheduling implementation will live in the yield function here. You can also safely assume that every thread of execution that is created with NQP thread create will call NQP exit at the very end. This will always be the last statement that the threads we're going to be testing in your code are going to do. So they are effectively saying, don't schedule me anymore, I'm finished. I'm not going to continue doing anything, so you can remove me from the queues that you have in your implementation. The other examples here, this one is a little bit more complicated in that it does more stuff. But this one is an exercise in doing some multi-threaded stuff with lots and lots of threads. So I'm going to pop over here. An NQP refiner, when you run it, looks like this as output. Each one of these tasks is its own thread counting. And then there's one thread that's responsible for doing the display part. So one thread is going to get scheduled to print out the current state of what each of these different threads is doing. Each one of these threads is going to be counting up by some random number each time. And then eventually the display thread will get scheduled, and it will then update the progress. And then all the other threads will get to go, and then the display thread will update the progress. And then all the other threads will get to go, and the display thread will update the progress. The other 2 that I've got here are NQP list insertion and NQP thread.c. NQP list insertion is code that may look familiar to you as something that we looked at in terms of multi-threaded list manipulation. This code exercises the worst case scenario of that list manipulation stuff that we were looking at. So this was that whole idea where eventually we start to lose nodes in the list because threads are getting interrupted halfway through doing the insert operation. But in this case, we're intentionally interrupting it halfway through the insert operation for every thread of execution. And so now it's the worst possible case here. This is meant to exercise your implementation of locks in addition to your own test that you're writing for exercising your locks. And this one is going to be a case where your lock implementation will have to work in the context of NQP threads. The other example that is given to you is NQP tasks.c. This one is a little bit different than just the AB operation in that the idea here is that we're trying to simulate different kinds of tasks as opposed to just having them all be the same identical kind of task. With the refiner example, every thread is doing exactly the same thing, and so every thread takes about as much time as the others do before it yields. With this one, what we're trying to do is exercise the idea that some threads are interactive. They're going to give up control of the CPU much sooner than other threads are. And non-interactive tasks are going to spend a lot of time on the CPU doing stuff, doing something before they give up control of the CPU. So interactive tasks are going to take about 1,000 microseconds before they give up control, and non-interactive tasks are going to take about 10,000 microseconds before they actually give up control of the processor, to try and give an idea of these are different tasks doing different things. The work that they're doing internally is just going to sleep, but they're all doing this sleep operation for a different amount of time. And because we're doing actual real-time clock stuff with the multi-level feedback queue measurements, what we should see from this is that interactive tasks appear to finish sooner than the non-interactive tasks are appearing to finish, because they're taking less time on the CPU before they give up control. So they get to get scheduled more often. They get their work done faster than the other ones do. I have set this up with some basic properties of the multi-level feedback queue settings here. These match what's in the assignment description, but you can also check to see if your other policies work with this implementation as well. This is one that should work with all the different policies. All right, I'm going to pop over to questions here, and I will step through this. So if we're always calling NQP exit after a thread is finished, how and why is our program supposed to get stuck in an infinite loop when using the NQP 2 threads policy? So this, I think this question is kind of partly about, and I might ask the person that's asked this question to help me understand this, but I think this is down here. I think this is about this. If the person that's asking this question can help me with this, I think it's about this. It's not a requirement that you get stuck in an infinite loop. The way that I tried to structure the rubric for this assignment is more like, this is a stepping level. So like if you get to this point, it's possible that we might need to terminate your code with Control-C, but it's not a requirement that we terminate your code with Control-C. Eventually, the goal is that the main thread of execution does get control back at the end. But if you were only able to get to implementing the 2 threads policy, I don't want to punish you for threads if you weren't able to get to the multi-level feedback queue stuff, because that doesn't seem like a fair way to assess that, that thing that I'm trying to assess you on. So if that is indeed the question, the idea here is that I want to have this here as kind of a stepping stone of making sure that I'm able to give you credit for working 2 thread implementation, even if it never does get control back in the main thread of execution. But I'm very happy to take more questions about that if I did misinterpret that question. For assignment 3, what is the main thread? The scheduler, the schedule creator. The main thread of execution is the one that's run by the main thread of execution is effectively the one that's the main thread of execution itself. So when this process starts, there's the main thread of execution in this system. The main thread of execution is the one that calls NQP schedule starts. And so in this case, what you would do, or how I would imagine you doing this, and the way that I did this is, when I call NQP schedule start, I also call get context, and that's my main thread of execution. I don't change it. I don't call make context on that one because I want it to appear as though it's going to return from that point where I called get context here. The main thread of execution is slightly different than the ones that you're working with in the create function because you don't have to call make context on them, and you also don't have to allocate a stack. There's already a stack for that thread of execution when the process started up in the first place. So the main thread of execution is the one that's running the main function in the first place. Can I explain why FIFO doesn't work for Refiner? For sure. So if I go back here and I change NQP Refiner to use FIFO, and I make this and I run NQP Refiner, the problem with this is ultimately that the main thread of execution is the last task to be added to this system. And if I'm doing FIFO, all the other tasks will finish before the main thread of execution ever gets to do anything again. And if the main thread of execution has to wait for all these other tasks to finish, it's going to appear to be frozen like this. None of them are doing anything because the main thread of execution isn't actually running right now. It's just kind of sitting here waiting around. It's printed something once and all the other tasks are in the middle of doing something right now. So in that case, because we have this main thread of execution being responsible for the display, or rather, I'm sorry, the display itself is a thread of execution, but it's still the last one that I'm making, still waiting for all those other threads to finish before it's allowed to do any more work. How does the join work? Do we loop until that specific thread is finished or swap context to that thread? For the loop in the join function, what I would do is just yield. There's no point in actually waiting for the thread to finish because the thread can only finish if you give control back to the other threads to allow it to finish. So the join function should effectively yield, check to see if the task is still in the system, and then yield if it is. If it's not still in the system, then it's finished. It's able to be joined. Does NQP2 threads never return to main? Again, I guess I have to emphasize that this default policy here is to make sure that if you only get the threading stuff working and you don't get too far into the scheduling part, that you get some credit for it. My implementation of the 2 threads policy is when I actually got to the point of implementing the round robin policy. The round robin and 2 threads policies are the same policy. They are the same policy. With the special case of 2 threads is that there's only 2 threads to go back and forth between. If you put 2 threads into round robin, it should behave the same way as the 2 threads policy because it's just the 2 threads going back and forth between each other. When I eventually implemented this myself, and I'm going to the discussion forum here because I wanted to just show what I put up here. I think it was here, yes. This is basically how I implemented yield and the way that I set up my scheduling policies. So at the beginning, 2 threads was its own thing, and then eventually I just switched it to be the same as the round robin function because it is the round robin function. Round robin and 2 threads will do the same thing in both cases. There's a tiny bit of C magic here. This is an array of function pointers, and what I'm using here is a feature in C that says I want to initialize this index with this value. So putting the square brackets around a number here or a constant will just say like this entry in the array will have this value. And then because this is just an array of function pointers, I can just use that system policy value that I have in the threads to look up that entry in the array and then call the function that I actually want to use for that. So in the end, the 2 threads function just can be round robin. You can just switch it fully with round robin. Nobody's going to assess the 2 threads policy if you've already got round robin working at that point. Given we don't have preemption, should MLFQ reduce priorities by more than 1 if a program runs for a super long? So no, you should just demote it to the next priority level if it's exceeded the amount of time for the priority level for that queue right now. So if it runs for like 5 seconds, you can just move it down 1 priority level instead of moving it down 10 priority levels. So the note about having the main thread being a special case for MLFQ is really about kind of the same thing as what's happening with the refiner example, where in FIFO it's just getting stuck at the end, but it's the opposite case. The main thread of execution in a lot of cases is going to be a super interactive task because it's going to join everything, check to see if they're in the queue still, and then immediately yield. And so it's going to spend like 0 time actually running on the CPU each time. And so it will always stay at the highest priority level, forcing everything else out. It's not required to have this as a special case, no, but you're just gonna see weird outcomes of this, where that main thread is just like, it's always at the highest priority level because it's joining and just spinning constantly and yielding. The special case that I'm describing here is effectively like, instead of putting it into the MLFQ system, just keep the main thread as its own reference and either always keep it at the lowest priority level, so have a special case in your boost to make sure that it stays at the lowest priority level, or alternatively, for MLFQ, just don't schedule it until there's nothing left in the system to schedule. Either of those is acceptable as a solution to this, but the effect of having the main thread just yield every time is going to keep it at the highest priority level. Yeah. Allowing it to stay at the highest priority, sure, yes, that would also be a valid solution, yeah. Oh, so that's actually something that was also addressed on the forum down here, I think. So Kai gave us a good answer for that. But yes, you can just cast the tasks to this type. You don't have to worry about the warnings for that. I think that might have been the last question, so that's good timing. So I think that I answered this question with the MLFQ one. So should the main thread be in the queue with all the other threads? You can, but with MLFQ, you might want to have a special case for that. Is it possible for MLFQ to be unfair depending on the allotment time at S? So it's possible, yes. So think about this for a moment. I'm actually going to invite you all to think about this for a moment. With MLFQ, what happens if S is too big? What happens if the allotment time is too big or too small and S is way too big? No answers. I'm not going to give you an answer. Oh, you can answer. Sure. Yeah, you can answer. What do you think?
Or something that takes a ton of time will get pushed to the back all the time, and it will never run in time.
If S is too high? If S is too high, eventually what can happen is kind of the same thing as the shortest time to completion first, where as new tasks are getting added to the system, the main thread in this case would just get pushed to the bottom of the queues, and then all the new tasks will just get to go in front of it because they're always going to be inserted to the highest priority queue, and then nobody will ever get boosted. So if S is effectively infinity, then we can't ever get to the point of having that main thread get pushed back up at the top so that it can get into round robin order with the other ones. So yes, it's possible for MLFQ to be unfair if we choose specific values for S in the allotment time. But in general, I'm going to assert that choosing appropriate values for S in allotment time will mean that MLFQ is fair. And that's it. Okay, awesome. I'll have a little bit more time for questions about assignment 3 on Wednesday's class, if you have more questions there. But as we saw in class, there's also some great questions that are showing up on the discussion forum. All right, so let's move on to something completely different. I'm going to ask you some questions about virtual memory stuff. I know that we're just getting into it this week, but I want to have a sense of where we're at with this as we're getting into this material. So I'll start the questions. All right, okay. So what even is an address space? The memory a process asks to use, I want to give some spiritual credit to that, yes. I'm going to be really pedantic about this though. This is the memory that a process is asking to use. So like at runtime, I'm asking for more memory by doing dynamic memory allocation. Like I want to have more memory in my heap space. The code, the heap, and the stack regions, that's also a fair answer. This has been just like beaten into you over the last 2 years. There's the code at the top, and then there's the heap beneath it, and then there's the stack at the bottom. And then there's the big question mark space in the middle that nobody ever talks about. But all we ever really talk about is code, heap, stack, code, heap, stack, code, heap, stack. And so I think that's a fair thing to choose. But the best answer here to me is the addresses that are available to a process to use. This includes addresses in the code region. This includes addresses in the heap region. This includes addresses in the stack region. But it also includes the addresses that are in that question mark area. The part that's in between the heap and the stack. This is still part of the address space for a process once it's started. So the memory a process is asking to use, yes, again, spiritual credit, that's fair. We do want to make our heap bigger, but we're really just talking about the heap here. Those 3 regions, that's also fair because that's all we've talked about for the last 2 years. But we really want to think about this as the entire set of addresses that a process is able to use in its execution. All right, okay. So this is fair. This is very fair. This is very fair. It's fair to say checking if a process uses unallocated memory. We all know and love the word segmentation faults. And somebody's got to do it. Somebody has to do that. Somebody has to make this decision about whether or not your process has tried to access something that hasn't been assigned to it. This is very directly related to converting virtual addresses to physical addresses. In an address space, and when we're talking about address spaces, the word virtual is effectively a synonym here, virtual address space. And I'm almost never going to say virtual address space when I'm saying address space. I mean the same thing. I mean them both to be the same thing here. For an operating system to be responsible for converting virtual addresses to physical addresses, it is possible for that to happen. It's possible for that to happen, but it would be so agonizingly slow that it just doesn't make sense for the operating system to be responsible for that. And part of this is, that was, at least to me, this mind-blowing idea, and this sounds really kind of silly in hindsight, but this mind-blowing idea that code is in memory. I don't know, like, this was just something to me that's just like, what does that mean, code is in memory? Of course code is in memory, but to run an instruction, you have to fetch it from memory, just like you were fetching data from memory. You have to fetch memory from data and put it onto the CPU. And so if our OS were responsible for fetching memory and putting it onto the CPU, and then taking that instruction and looking at the addresses that an instruction refers to, and also translating those, that would effectively mean that to run one single instruction on our CPU, our OS would have to take the virtual address of the next instruction that our program counter has, convert that to a physical address, read the memory, load that memory onto the CPU, take the operands for that thing, figure out what those virtual addresses are, and possibly load more stuff. And so to do one single instruction, our OS would have to be going through 5 or more different instructions just to get that instruction on the CPU. So our hardware in this case must be responsible for this. The operating system has to tell the hardware what to do. And the way that the operating system tells the hardware what to do is by having additional information in our process control block. The additional information in our process control block kind of changes based on the type of virtual memory system that we're doing, because it might be that our operating system merely needs to say the virtual address space starts here, end of conversation, all the way up to these different parts of our virtual address space are located in these completely different locations in physical memory. but the hardware itself is the one that's going to be responsible for doing the translations. So our OS needs to keep track of where processes are and where their virtual address spaces are. And directly related to that is keeping track of the free space and physical memory. So what has actually been allocated to a process and what has not been allocated to a process, what's free for other processes to use. Is that okay with everybody? Okay, all right, awesome. Okay, all right. I want to be picky about my use of words here. I want to be really, really picky about my use of words here. These two here, handling memory access exceptions and keeping track of exception handlers, they look real close to each other, but they mean subtly different things. Keeping track of exception handlers to me is, here's a list of the functions I should call when an exception happens. Someone has tried to translate an address that they haven't allocated. They've tried to dereference null. They've tried to read page or entry 0 in my virtual address space here. Our hardware knows what to ask the operating system to do in this case. When our OS starts the machine up, it'll say, hey, when somebody tries to access memory that it hasn't allocated, here's how you tell me. Call this function, start running code here, and put these values in the registers so that I know what to start doing. But hardware can't handle memory access exceptions. And when I say handle here, the hardware cannot kill your process. It can't terminate it. It doesn't even know what a process is. It can't terminate a process because it doesn't know what a process is. I'm running Linux on my system right now, and I know that many of you are running Windows or Mac OS. And in a lot of cases, our operating systems are somewhat interchangeable on these things. I could run a version of Mac OS on this. I could run Windows on this. And in all three of those cases, the process control block and the thread control block are completely different structures. This is an x86 machine. I don't know where I'm going with that. It's an x86 machine. There's a real hacky way to get Mac OS on it. That's what I'm trying to say. Yeah, sorry. In all of those cases, though, the operating system has its own structure for what the process control block looks like. It has its own structure for, like, this is the list of running processes on the system. And the hardware doesn't know, and it can't know. It can't know because maybe someday I want to make my own operating system, and maybe someday you all want to make your own operating systems, and Intel doesn't know about that, and AMD doesn't know about that. And Apple making Apple Silicon doesn't know about that, but they can support it by having us be able to tell them to tell us what to do when this sort of thing happens. So the main thing is it can keep track of these exception handlers. It can have some hardware and some memory to be able to say that when an exception happens, start running this code. And the other part is having additional registers. From our perspective, having some additional registers as an operating system. Again, we're starting to step on the toes of Comp 3370 here. When you get into Comp 3370, that's when actually figuring out how the address translation stuff actually works. It becomes important. For us, it's just, hey, there's additional hardware registers for us to set when we switch something onto the processor. This is going to be a bit of a change up and a shake up here right away. Okay, Johanna's right at the top, Bossman, Jack, and Tiger Baby. These are very creative names. Okay, so our next few questions are about our virtual address space itself. So the virtual address space is consisting of the code in the heap and the stack section. And so I want to ask questions about the code in the heap and the stack section here. Okay, all right. I'm going to give some spiritual credit to this because so many people picked it. Spiritually, sure, yes. When you compile your code, you're getting all these assembly language instructions set up so that it is going to be what the code section is ultimately going to be populated as. However, the thing that's responsible for actually populating that address, that part of the address space, is the OS. When I do exec on a piece of code, on a file, I'm asking the operating system to take this inert file that my compiler produced and stick it into that code section. Fully replace the code section for my process with this code section that I'm asking you to replace it with. Your parents, when they run your program, is a little bit of a joke, but when, I'm gonna come back to this Mentimeter in just a second, I'm sorry. This image here is the front of a machine that's called the Altair 8800, and this toggle switches that you see just below these red lights, so these ones here, these are literally the switches that you would use to change the contents of a memory location in binary. And so to load a program on this computer initially, to get it set up so that you could have like a tape drive start feeding stuff into it, you would have this yellow switch here that says examine or examine next, and then there's another one that says store and store next. You'd press that switch to get to location 0, and you'd start inserting instructions. And then you'd press a toggle to go to the next one, and you'd toggle the instruction in binary, and then you press a toggle to get to the next one, and you'd fill up main memory this way. And so at some point it was the operator's job to actually fill up the code section of our virtual address space or our address space here. And those would have been our parents, probably my parents more than your parents, but parents nevertheless. We got 2 more questions here. Okay, oh gosh, we were on different wavelengths today. Who is responsible for populating the stack section? I'm gonna give some spiritual credit to this one. In this class, we've now repeatedly said, hey, you start this thread, and when the thread starts, this is the bottom of the stack. I want you to use this function to be the bottom of the stack. And in the assignment that I'm asking you to do, you have literally created memory for a stack, and you are the operating system here. You've made some memory for a stack, and you said, this is the bottom of the stack. I'm going to argue that, and I want you to think all the way back to Comp 2280, if you have taken Comp 2280, where one of your assignments, I believe, please correct me if I'm wrong, but I believe one of your assignments was build you a call stack, or at least some part of an assignment was build you a call stack. And you were writing the instructions to do that. And that is effectively what the compiler is going to be emitting on your behalf when you compile your code. So your program and the standard library, again, spiritual credits, you are invoking functions in your own program and they are adding stack frames. But the compiler is what would have been responsible for setting up the stack in the first place, pushing stuff onto the stack so that when it gets called or invoked, then it's going to have those values put into the appropriate registers. You're squinting your eyes at me as though you're trying to say, no, you're wrong.
When you say populating in putting the memory addresses, or in this case, populating is putting them on the hard drive.
Okay. You're right. I'm saying that the compiler is making the code that's inert sitting on the disk, and you're saying that the instructions that are actually being invoked as part of your process are what's populating the stack. That's fair. And I'm gonna put my cursor over this, and I'll put my thumb over it, and then when I'm looking at it, I'll just pretend that there's a green check mark there. Okay, yeah, sorry, that's the best I can do in the moment. Here's our last question. Now I feel like I'm going to offend everyone about pedantry here. Okay, I'm going to assert that the hardware does not know anything about the heap. The hardware actually has no concept of your virtual address space. You can put the heap wherever you feel like it. I'm going to make that assertion. You can just jam your heap in any location in your virtual address space if you had the control to do that. I'm going to further assert that partly, but not as much as you think, the OS is responsible for this. So I'm going to give some spiritual credit to this option. The operating system does have some responsibility for saying that the process has allocated this part of its address space, but that's it. And it's even less than you think it is. There's a lie that you've been told over and over again, including in this class, that is, when you call malloc, you are asking the OS for memory. That is not the case. You are indirectly asking the OS for memory, but you're not asking the OS for the memory. You're asking your standard library for that memory. And one exercise that we can do tomorrow at this point, that we'll do tomorrow, is if I call malloc a million times, how much do I actually ask the operating system to do? And it's surprisingly little. It's not actually that much. The standard library itself is going to have the primary responsibility for dealing with responding to requests for heap space, which is malloc that we're calling to it. And in some cases, depending on the standard library and the allocator that we're using, it may never ask the OS for that space. It may pre-allocate that space in your address space before it even gets to the point of asking the OS for those things. And so in this case, I'm going to stick with it's your own program or the standard library that's ultimately managing the heap itself. This is just like giant shakeup every time. All right, okay, so congratulations to Bossman Jack, whoever that happens to be. I guess we're in the same wavelength for thinking about stuff. And then Kathy and Stingalicious there, so good job. All right, so we are at the end of our time for today. And so we will start taking a look at this stuff tomorrow. But what I am going to say is that at this point, you should be able to evaluate the performance of scheduling policies, and you should be able to compare and contrast different scheduling policies. And then what we're going to start doing tomorrow is taking a look at some different mechanisms for doing virtual address translation. My ultimate goal for us for this week is that I want to be able to take this wild ride through what happens when I do a null dereference all the way through the OS, getting to the point of the word segmentation fault core dumped being printed in our terminals. I want us to be able to describe this whole flow of what's going on in the whole system. And it's going to involve a variety of different parts of the course as we've seen it so far up until this point. That's it for today. I hope that you all have a great rest of your day, and I will see you all tomorrow. Bye, everyone.